So we're gonna talk about about cut matching game today. Is again, why do we talk about it? It's like a foundation of like how we gonna get fast algorithm for the whole thing that we have been talking so far. Okay, and can anyone recall what is a cut matching game? Like there's gonna be a round. In each round, what will happen? Yeah. Okay.
Cut player tries to select a cut so that when the matching player like puts any arbitrary matching on, it's still adding a relatively high amount of like useful edges that are making the
Right. It's useful in the sense that at the end, no matter what the matching is, at the end you kind of get an expander, right? So yeah, in each round, a cut player choose AI, BI, and then the matching player choose need to match all of the AI to BI. Like BI can be bigger, but AI, the smaller set, need to be all matched in some arbitrary way. And we want that which the cut player choose this thing so that no matter what, after a few rounds, then the union of this matching is the expander, right? Okay, that is, yeah. We're gonna show how to choose A and B in round I in time ni time, so that after log square rounds, then this all one node weighting is expanding in the graph. Okay, and so if you spend ni time for each round and there are log square rounds, the total number of time is something like n log to the fourth. Okay. And okay, we talk about how the strategy to make this to achieve this, right? And so we define this pi of a. Pi of a is basically kind of the probability distribution that end at A after round I. When we perform one specific kind of random walk, do you recall what is that random walk? What is the process that define PI?
Yeah. You would go through each round, and if some node was not matched, then it just stays put and you continue with that node on the next round. But if it was matched, you kind of walk from it with probability 1/2.
Exactly. Good. Yes, exactly. So that will just define PIUV. This is just the probability that if you start at U and you end at V after round I. And this is just kind of the vector that you of how each of the U end at A after round I, right? So this is a probability distribution. You can.
Yeah, is a matrix. So we're looking at some column, right?
Yeah, this is like a column. Yeah. So column of PI at column A. So this is, and so you can think of this as the distribution. Overall U, how much mass n at A after round I. Okay. So once we have defined this, then you can think of each node A as a point in n-dimensional space, right? Because this is like a vector of n dimension. Okay. So, and we have defined one potential function and that potential function is such that if that potential function is small, then we can guarantee that all one node weighting is expanding. What is that potential function? Yeah,
the sum of square differences between the distances.
Yes, sum over all nodes. the distance from what to what?
Or I guess from the position, like position minus average squared.
The position, sorry, again?
Minus the average.
Minus the average, exactly. Square, yeah. So you kind of measure how much this thing, the point, is further away from the average, okay? And this is square, and sum over all nodes. And we see that if this is tiny, like if this is 0, then it means that this is all, like you basically mix completely, but we have seen that if this is, then if this is like a polynomially small, then this is expanding, like 1/2 expanding. Okay, so now the goal of today is to show how to achieve this in fast time. Okay. We also talk about how, like the strategy of how would we, like at least the intuition of how we want to choose AI BI. What's the intuition? What's the heuristic that you want to choose? How you want to choose it? Okay.
Relatively spread apart clusters.
Exactly. Yeah. We want to choose AI and BI that are far away from each other, so that when you, okay, good. Because when you choose, if this is a point A and this is a point B, if there is, if the matching player add a matching between A and B, then how does A and B, the position of A and B is updated? You recall this? Yeah.
Would it become the midpoint? Or?
Yeah, it's just gonna become at the midpoint. Yeah. So the new position is just at the midpoint. So each matching just average the 2 points together. And so we kind of, so if the potential function is to kind of get everything close to average of the whole set, then if you choose the guys that are kind of far away, then both of them will come significantly closer to the average. Okay, so that's the intuition. So if you choose the guys that are far away from the average, both of them, they will both come close to the whole average, okay, to 1/n. So we want to choose large set AI and BI. Both should be large so that we match a lot of things. And these two sets, it should be such that all of them are far away from each other. That's the intuition. Okay. And but this is a good intuition, it's correct too. And but the thing is that we cannot afford to just work on this large space. When you have n-dimensional space and there are endpoints, there are just the total of information that you need to process is n square numbers. But you want to spend time something like n. That's impossible. So the idea is to actually to project all the points to low dimensional space. Okay. So the idea is like we're gonna choose some random direction, and we're gonna project all the points to this line. Okay. The thing is that once you project the points, the guys that are far away from each other might come to here, and they become close. So it's not clear that this works. Like you kind of destroy important information, right? We kind of want to choose pairs that are, we're gonna choose A and B that are like pairwise far away from each other. If you project it down, now you don't know whether it was far away or not. Okay. So, but the key thing is that if you choose a direction randomly, then you can, in like a strong sense, say something that this distance is gonna be quite preserved. So we see formalization of this now. Okay, so let's be formal today. Okay. So here is the algorithm. Like here, let me present the algorithm precisely now, and then let's see that this algorithm actually is fast, and then analyze the correctness. That's what we're gonna do today. Okay, so in round I, okay, what we're gonna do is first choose a random n-dimensional unit vector, Ri. So think like you have a sphere in n dimension, and you just choose one random direction. This is Ri. Okay. You can ask how to do this in computer, but like you can do, for example, just choose a random Gaussian with like high enough accuracy. Like this is a real number, so you cannot afford to do this, but let's ignore that. Like once you choose a random Gaussian with high enough accuracy, then you can get this thing. Okay. Okay. And now, what's next is that we're gonna compute this thing. Okay. So what is this? This is just basically a position of all points projected down to R, right? So the position of V project down to Ri, that's the position of XV. That's like the position of projected position of V. That's XV. So X is, and you write this in like, just kind of put all the vector together. That's like matrix. So this is like a one vector X. Okay.
So we're gonna do this for all points, or?
Yeah. So right now it seems not clear why this is fast, right? Because you cannot even afford to write down P I-1. We'll see soon. But at least this is the meaning of X. Okay. Okay. So X really is just like look at the position of all point at time from the previous round I-1, project it down to direction Ri, and basically now all the points are kind of sorted in, you have xv1, xv2, xv3, and so on, and xvn. They are now sorted in this line. Okay. And then I'm gonna choose a median threshold according to x. Okay. So choose threshold eta, so that like, yeah, it's a median basically. Okay. So choose a median so that there are like n/2 points here and n/2 points here. This is eta. Okay. And your AI is just going to be the one on the left. BI is the one on the right. Okay, that's the algorithm. And currently, since we choose it to be median, so AI and BI are of both sides n/2. So when the meshing player chooses a meshing, it will actually choose a perfect meshing. It needs to choose a perfect meshing. Everyone needs to be meshed. Okay. Okay. Is the algorithm clear? That's the algorithm. Yeah.
For the first step, could we choose an arbitrary vector instead of a random vector?
No, it needs to be random. Yeah. It needs to be uniform in this sphere. right? Yeah. You see soon, yeah, why? But the idea is that if it's arbitrary, you might distort the distance after projected like in arbitrarily bad way. Once it's random, then you can say that with in expectation everything is good. Yeah. Yeah.
What if there's no perfect matching? Then what's then?
What if there is no perfect matching?
Yeah, like there's no perfect match between A and B.
No, like know that mi is not in a graph.
Oh, it's not in the. Okay.
Like this is you choose a cut, and then matching player will need to choose some new matching to add to the graph.
Oh yeah, right.
Right? Okay. Okay, good. So now let's see why this is fast. Okay. So first, this thing can be done in linear time. Again, the idea is like for each coordinate of Ri, just choose it to be a random Gaussian, and then make it unit vector. So that you will be for each coordinate of Ri, just choose a random Gaussian, and then it might go maybe here, and then you make it unit. So then it become here, something like that. So I will not go over this. And this part, choose a median. You can sort all the x too, and then you pay n log n. But if you want just a median, you could actually do it in linear time. There is a nice algorithm to do this. You can learn it. Yeah. But we don't really care whether you pay n log n or n. Okay. And then this is also linear time. Okay. That's clear because you can just compare all the x value with eta. So the only thing that is not clear is this. Okay. Why this is fast? Because we cannot even afford to write down pi minus 1. Okay. So let's see. Okay. So how do we compute x fast? Okay. So to do this, we're gonna look at the structure of pi minus 1 more carefully, and then see that when you don't need to what we want is not to write down pi minus 1 explicitly. We just want to multiply some vector to pi minus 1. And if you want to multiply some vector to pi minus 1, you can do it fast. So why is that? So suppose that let I denote bold mi to be the matrix that capture how the random walk step is that capture this random walk step through the matching mi. So what I mean is that it's a matrix, some matrix, okay, such that when you multiply it to pi minus 1, you get pi. So it captures basically how you move points after you get the new matching. So what I mean is this. So you recall that P is just going to be pi minus 1 if A is not in the matching, and it's going to be the average of its match edge if it's in the matching. This is how you define pi from pi minus 1. And I'm gonna just write a matrix mi in such a way that when I multiply mi to pi minus 1, then I get pi. How does this matrix look like? It's going to be simple. It's going to just have on non-zero in this matrix. How does it look like? It looks like this. Look at each node, A prime. If A prime is not in MI, in the meshing, then you're gonna just put 1, like at the diagonal. This corresponds to like how you set that when you just set the vector to be the same, right? And look at each of the matching edge A, B. You have A and B in the matching. Then you look at the column correspond to A, column correspond to B, and the rows correspond to A and B. How it looks like is just gonna look like this. You put 1/2, 1/2, 1/2, 1/2 here. Okay. So each row and column, there are like basically at most 2 non-zero in MI. So hopefully you can just try to verify this yourself that this is exactly the matrix here, such that when you multiply this to this matrix, then you get PI. Okay. So, but it's a simple matrix with just ON non-zero. Okay. And you can see that when you want to multiply a vector to this matrix, when you multiply a vector to any matrix, you can do it in non-zero, like in time proportion to the number of non-zero of the matrix. Okay. So that's the basic fact. Okay. Idea is that you can just, yeah, I'll not go over this. Yeah, you can multiply any vector, like a vector to any matrix in the time proportion to non-zero of the matrix. Okay. So you can multiply V to MI in ON time. Okay. And actually for MI here, for this particular matrix, you can even think of the really simple process to multiply V to MI. How? Like you really just look like the concrete process really is just this. You have this vector V, then you just scan through all the edge in the meshing. And what you do is that for each edge in the meshing, you just assign it to be the average. Assign both new value of VA and new value of VB to be the average of VA and VB. So that's what happened. Okay. So this is clear that you can do it in linear time. And now observe this. If you write PI as PI minus 1 times MI, it means that you can write PI as like unfold this thing. Then you're gonna get MI here and then PI minus 1, unfold MI minus, and then unfold this thing, you get MI minus 1, MI minus 1, MI minus 2 up to M1 here, and then P0 here. Okay. Just unfold this. What's P0? P0 is identity. So that's just, you can think like you can remove this too. Okay. So PI really is just multiplication, the product of M1 up to MI. Okay. So now, can you tell me why can we compute X, which is Ri times Pi minus 1 fast? How to do this? Okay.
Because we have this expansion for PI, we just start like for each matching that we have, and we have I matchings, we just do that process, which is O of n time.
Exactly. Just multiply the random vector R to M1, you get one vector, you multiply it to M2, you get a new vector, and repeat. Each of these takes n time. There are I iteration, so that's ni times in total. Yep.
Could you also explain why the non-zero, the number of non-zero elements in MI is all vacuum.
Oh, sure. So if A is not in a matching, then I claim that everything here is all zero. Like that's the structure of M. Like there is just one here, and everything in this column is zero. Okay, and if A is in the matching, then there's gonna be just two non-zero, just half and half. Everything else is zero. So every column has one or two non-zero. So that's why there's just 2n at most non-zero. Okay. Okay, so yeah. So we can compute this thing in times n times I. Just multiply the resulting vector to each mj one by one. Okay. So now I hope you are convinced that at least this is fast. So let's now analyze why it's correct. Any question up to this point? Good. Right, so what we want to show is this. If we follow this algorithm precisely, choose a random vector, project everything down, and then look at this line that you project, then cut at the median. Just do this. After log square round, the potential function will be small. And if this is small, then we are done. We have proved this. Okay. And our plan is going to be this. Okay. Our plan, the high-level plan, is to say that we want to lower bound the potential decrease. What I mean is that for every step, every round, the potential function decreases by a lot. That's what we want to do. So what we want to say that this is a potential decrease. Like look at potential from the previous round minus the potential on the next round, which is like lower. This is like potential decrease. This thing should be big. How big? It should be big compared to, like, proportion to the previous potential over log n. So in each iteration, you reduce the potential by like 1 over log factor. This just means that the new potential is going to be at most 1 minus 1 over log times the old potential. Okay. So, and then, so it means that this is like the new potential at round I is going to be 1 over log, 1 minus 1 over log to the I times n. Because the potential at time 0 is at most n. And once we have this, it means that if you repeat log square rounds, like when this is like, when I here is something like log square, then this whole thing, let's say it's 10 log square, then this whole thing is just going to be at most like something like n over 10. Okay, so then like this is going to be small. Okay. You need to choose a constant here to be big enough according to this thing. So here I use the fact that like this thing is at most e to this thing, right? 1 over log times I. Yeah. Because 1 minus x is at most 1 this thing for all x. Anyway, yeah. Okay, good. So that's the plan. We want to do this. And let's formalize this plan. Okay. So let's understand how the potential decrease. And I claim that the potential decrease is actually going to be really what our intuition says. We say that we want to match between pairs that are far away, okay? And the potential reduction is just going to be like the total distance square between mesh nodes. So the further pairs that you mesh, the further away the pairs that you mesh, the bigger the potential decrease. So in like formally, you can say this: for every edge that you like for every matching edge, AB in MI, when you match this edge, when you match A and B, meaning that you move the point from A and B to both of them to the average. That's how you move points. I want to look at the potential at the time when A and B is on the different point, and then you put both of them to the average and see how much that changed the potential. Okay. So this potential decrease is just going to be exactly this thing. The potential decrease after updating the position of A and B, meaning that you just average them, just going to be exactly the distance between A and B square with some scaling factor. Okay. So to interpret this, it just means that you basically want to match the guys that are far away, like what we think, what we have thought. The further away the position of U and V are, the bigger the potential decrease. Okay. So this means that the total potential decrease in round I, this is the total potential decrease, it's just going to be exactly summing overall meshing, and then the distance between the endpoints of the meshing edge. That's exactly how it looks like. So now we're going to prove this thing. Let's prove this. Okay. So this lemma 4.5 really like give us really precise understanding of how potential decrease. Okay. So let's now prove 4.5. Okay, so to prove 4.5, I will need this fact. Okay. It's some algebra. Okay, it says that if you take any vector u and v, let's say they are in the same dimension, in the same space, and then we're gonna have this. The size of u square, the size of v square, minus, this is like average of u and v, right? Average of u and v square, like minus 2 times average, the size of average square, is just going to be exactly 1/2 of the distance between u and v square. So why is that the case? Yeah. Okay, good. This is because, well, like, you can see that this is u and v are vector. Let's say that I look at coordinate I of u and coordinate I of u, coordinate I of v. If I look at this thing, minus plus vi square This is exactly what? This is exactly 2 ui square plus 2 vi square. Right? Like the cross term from these two just cancel out. And you get twice of this. So it means that if I just sum this, like sum this overall coordinate I, what we're gonna get is just exactly u square plus okay. This is just sum. This thing is really just summing over all this thing over all I. Okay, and now I just can scale down by half. Take this 1/2. Take this 1/2. And then we can say that, let's say I put this thing to be 1/2, and then now I need to multiply by 4. So that is just, this is 2. Okay, so that's it. Okay. Now I just rearrange to get this thing. Okay. So how do we use this fact? Okay. So let's see how does the potential change? So, like, when you change after change by the matching edge A and B in MI, the change of potential, Well, like, we know that the potential of I claim that this is the potential that A and B contribute to the potential at time I minus 1, right? And then, but like the new potential is just this thing. Minus yeah, like imagine that I consider this thing. Let's call it prime. This is like the potential when I just move only A and B to the average of A and B. So how does this change? Every other point stay at the same point. So this cancel. And the only thing that you need to consider is just the position of A and position of B. How does it? Do you agree with this? Okay. This is how the potential change because of A and B. Okay. The potential, how it decreased because of A and B. Okay. So, but you know that these things are the same point. When you move A and B, you move like before they were not at the same point, but after, because of the matching, the position of A and B at time I will be on the average. Okay? So you can write this as actually minus like the same thing, 2 times the average. A the average minus this thing. I can replace this by this thing. Okay. Good. And now I can just also write it down like, write this, just rearrange it a bit so that it really look like, okay, this thing plus this thing. It's just the same thing. Okay? I just kind of spread what I minus n to both of this term. Okay. Okay. So now we can apply this lemma, this fact. How? How would you set U and V? If I set this to be U, set this to be V, you can see that this is exactly, this is exactly U plus V over 2. Okay. So this is going to be then, like this whole thing is then equals to 1/2 of U minus V. What's U minus V? This is just the distance, like the difference between position of A and position of B, of B. So you get, yeah, you get this thing. This is exactly U minus V square. Okay. So we just proved lemma 4.5. Question about this? Good? Okay. So, okay. So that's how we understand like how much the potential change. We want to basically really formalize the intuition that we want to match the guys that are far away. Okay. So now next one. To understand what's going on, I tell you about like important thing about the property of random projection. Okay. I want to say that random projection preserves square distance. Okay. And here is a formalization of what I want to say. So let's say that R is a random unit vector, like what we choose. Okay. R is like a random direction. Okay. Then if you take any vector V, so think of V as like V as is a vector, but think of V as like the kind of the difference between 2 points. That's V. Like if this is point A, point B, V is this vector. Okay. Okay. Think of V as this vector. Okay. So what you have is this. If you look at like when you project V to R square, this is like the size of V after projecting to R. the size of V square after projecting to R. This is basically the same as the size of V square, but with some scaling of n. And that makes sense because you are living in n-dimensional space. You project it down to like a one-dimensional space. So like think like now everything is just scaling down by a factor of n. But if you ignore this scaling factor, what this says, like morally, is to say that the size square of each vector in expectation is preserved. Okay. The size square is preserved. The norm square is preserved in expectation. So in expectation, things are really the same. Not just that, we have like a nice tail bounce. So what it says is that if you look at the probability that, so think of alpha as log n. You look at the probability that the size square is much more than the expectation by alpha factor. So that probability is exponentially small in alpha. So if you think of alpha as log n, the probability that the size square deviates from its expectation by log n factor, that's something like, when this is like 100 log n, this is like 1 over n to the 10, something like that. So this is going to be tiny. Okay. We will not prove this. I will just assume this. Yeah. It's about some like random process of like random behavior of this random projection. Like this is like it just says that this kind of looks like Gaussian. Yeah. Okay. Any question about the statement? Okay. So now let's apply it in our context. Okay. In our context, think of this, like recall that we have this is the position of A, and you multiply by R. This is like projected position of A. And you have that, like, let's say that mu is the average position, like projected average position. So this is average position, which is 1 over n. And then I project it to R. So mu is like projected average. Okay, that's mu. Okay. So I claim that we're gonna have this. We're gonna have that. First of all, like if you look at the distance, the square distance between A and B, okay, they are basically kind of the same as the square distance in projected after projection. But like in expectation, they are the same actually. Yeah, in expectation, these things are the same. Like without like just 1 over n times this thing. In expectation, they are the same. But the projected distance square will deviate from the expectation by log n with low probability. Okay. So with high probability, they are within log n factor to the expectation. Okay. And I can say the same thing here, like the distance between the points to the average. We have this in expectation, and you can say the same about like it deviates from expectation by log n factor with low probability. So why is that? How do we prove this? Well, like to get this thing, right? I just let V to be this vector. V is this vector, and then you get that like this thing is really just like R times V. Right? Because Ri. Yeah. So I set B to be this vector. Then you can see that like Ri times V, which is really just x a minus xb. And then once we apply this thing, then you get this thing. Okay. Why? Like, I mean, you basically choose alpha to be big enough, like 10,000 log n. Then the probability here is going to be like tiny, something like 1 over n to the 100 or whatever. And then you can do union bar over all n square pairs. Okay. So with high probability, you get this thing. With high probability, you get this. Okay. And for expectation, you just set V to be this one. Sorry, for this one. Yeah, for the second statement here, set V to be this, and apply this fact. Okay. Okay. The point is, yeah, if you choose any 2 points, look at the distance square. This distance square between any 2 points is going to be preserved after random projection. That's what you should think about this. Okay. Question about this? Yeah.
It's not preserved exactly. It will be preserved with the scaling of n, right?
Yes, preserved with scaling of n. Yeah. Yeah. Okay. So now we are ready to do everything. Okay. So let's now analyze how the potential change. We have seen that the potential change is just exactly this thing, summing or matching, and then the distance square between the two endpoints of the matching edge. Okay. But this is going to be basically something like this. The distance square after projecting, but with some scaling. There is a scaling of n here, and I get log n here, where c is like a big enough constant, so that this is true with high probability. In expectation, you just need this. This would be equal in expectation without log n, but with log n, this is true with high probability. Okay. And now we have, let's look at this one. Okay. Let's look at this one. Right now, all the nodes are in the line. X, V1, X, V2, X, Vn. And this is like A, I, this is Bi. There's a threshold here, eta. Okay. Let's look at one pair in particular. Let's say this is a XA, XB. Okay. So XA and suppose this is in the matching MI. Okay. So this thing square, right? It's just going to be at most, it's at least this part square and this part square. So this, maybe I use color. This. Okay. So without square, this would be equal, but with square now it's strict. Okay. So you have this one. Okay. And now, once you have this, you basically just sum like for all nodes. Like I claim that this is now the sum over all nodes. From all node U, the distance from all node U to the threshold eta square. Why is that? Because MI is perfect, right? So every node U will contribute to something here. Okay. Right? Every node on the left side will be contributing here somewhere. Every node on the right side will be contributing from somewhere here. So this is now actually sum over all nodes. Okay. And now, okay. So this looks quite familiar to you. This is sum over all nodes, distance squared to the average. Not average. This is not quite average, right? This is just a median threshold. It's not the average, not the same thing.
Wait, would the median threshold be the same as projected average, or?
No. So for example, let's say that maybe let's say this is 0. Okay. And then let's say that I have 10 points actually here. Okay. And then maybe just 2 points that are far away. Like this is -1 here. But this is 2 points here that are like something like at position 10. Then maybe just 1 point at position 10. Okay. So there are 10 points of position -1, 1 point at position 10. Sorry. This is 10 points. This is 1 point. What's the average? The average is just 0. Right? You have like a 10 of -1 plus 1 of 10, sorry. So the average here is just 0.
The median is way to the right, right?
Yeah, but the median is now like, the median is actually here. Because the median, it need to be like cutting between, like, it doesn't really care about, it need to cut like the node set into half and half, right? So like you have 10 points here, so it need to cut like maybe 5 points here. Yeah. Make sense? Yeah. So eta, the median, and the average are not quite the same. But this is quite something that looks almost like what we kind of familiar with. But you see, you can say that this thing, you can replace eta by the average here. Why is that? Because if you think of the average as the optimization point, it really is just the point that minimizes this distance square. This is like another definition of average. It's just the point that minimizes distance square. That's what the mean is in the geometric setting. So it's both like the sum of everything divided by the number of points, or it's just the point that minimizes the distance square. Okay, so this is like a minimizer of this term. So you can low bound it by the average here. And now this looks really even closer to what we have been talking about. The potential function is total distance square. Up to now, we get that this is like distance square to the average too, but in the projected space. Okay. So I want to say that this is something like if with our projection, it would be just this thing. Just the potential function. Okay. So let's try to make it formal. You know that this is the total. This is like what? The total distance square to the average of all points. At least in expectation, when you scale this thing up by n, it's just the same as the total square distance to the average before projection, right? This is a property of random projection. This thing is the same here. And this is just exactly the potential function at time I-1. Okay, so let's try to combine this thing with this whole thing. Okay, so what we get so far is that, let me put the expectation to here, and then I get the expectation here, right? So it means that the expectation of the potential decrease is just going to be potential function at time I-1 over log n, right? Because this thing is just 1 over c log n potential function at time I-1. Okay. Why do I need to have this term actually? It seems like I can just put expectation and then I get this thing. Why do I have this thing? This is tiny, like it's really something like 1 over n to the 100, but it must be there. Why is that? Yeah.
Does that come from the fact that, well, what you wrote above, that the salmon has the projected position? Is that, but like the potential function has the actual position? Does that come from this fact, or?
It's related, but like that's not quite what I'm like the precise thing that I'm looking for. So when we have this thing only with high probability, with probability like 1 minus 1 over polylog, 1 minus 1 over poly n. Like this whole thing hold with high probability. So like this is like to modulo the fact that we like to assume that this is like to take account with like that this event, this inequality only holds with high probability, we need to put this thing too. Okay. Try to convince yourself that you need this formally. Okay, but once you have this, we are done. We are basically done. Think of this as something negligible. Okay. Why? Because you just rearrange, and now you get that. In expectation, the potential at time I reduced from the previous potential by 1 minus 1 over log plus something tiny. So it means that after log square rounds, this potential must be small as we want. Yep.
So you mean that before we add the 1 over poly n, it's only true with high probability?
Yeah.
But after we add it, so wouldn't it still be true with high probability?
This is now true, like this is now true, yeah, like just with certainty. This is like the deterministic statement. But this whole thing is with high probability. Okay. All right. Okay. Yep. Okay.
So we're basically up the entire calculations above, we're like not taking expectation yet. We're saying like with high probability this is true, and
Yep.
when we in the next bullet point we actually sit down, take the expectation, and that's where we incur the loss.
Exactly. Yeah. So in particular is this one that this is like only holds with high probability. Yeah. Okay, good. So we are done. We now get that the potential decreased by 1 minus 1 over log. So after log square rounds, the potential is small. Once the potential is small, we have proof that all one node weighting is expanding. Okay, and here is some, to make sure that you really understand this, try to convince this. Suppose that right now my strategy is that I project it down to, project points to the line, right? And then I just choose a median, and then say that AI is everything on the left, BI is everything on the right. What if I change my algorithm to the following? Just take like the smallest n over 10 guys here and smallest n over 10 guys here. Okay. Then that's AI, that's BI. Show that this works. So at some point in the calculation, we at least one line we use that MI is a perfect matching, but try to convince yourself why this works. It's nothing much really, but like you should be able to like go through this and see that how to make this work. But you can see that if with the blue choice here, really it still captures our heuristics. A and B are still big. It's still constant factor big, and they are far away. Like if I choose A and B to be like the one that is like closest to the median, that shouldn't work, because there can be like a lot of guys here that are already close to each other. That's not good. But if I choose AI and BI to be the group that are far away, that should be good. So try to prove this. Okay. Any question? Okay. By the way, there is one possible project that I want to mention. Like there will be actually a bunch of possible projects related to cut matching game and its application. So I'm just start to list the concrete thing now. So first thing is that do we need a fresh random direction Ri in every round? So imagine that like if I choose Ri for one round and I just reuse this random direction for each iteration, I don't think that will work. That shouldn't work. But what if I say like I choose this random direction R1 and then I use it again after log n rounds? Maybe things are fine. I don't know. But why is this good? Because suppose that you can reuse them. Like suppose that you need to generate only like k many random direction. Then you can go through the analysis and you can see that the running time is now gonna be nk log square. We used to set like k to be like just the number of rounds, so that's gonna be n log to the fourth. But if you can reduce k, then it will just immediately speed up this cut matching game. And this is the fastest running time known for cut matching game. So if you can improve it, it's kind of good. Okay. All right. So let me mention one more thing. So far we talked about how to make sure that we want to construct G so that like G in the such like we want to construct the graph such that all one vector is expanding. What if we want to guarantee that like something else which is not all one? What if we want to guarantee that a node weighting A is expanding? Some other node weighting that's not one. Okay. So we can do it too, but to do that, let me introduce something. There's a word like that people use in literature called B matching. B matching is simple. So just think of B as a node weighting. Okay. So B matching M is just a graph such that the degree respect B. That's it. So you can see that all one matching is just a normal matching. Right? A matching is really literally just a graph such that every node contains at most degree 1. And so all one matching, all like 1V matching is just a matching, normal matching that we have been talking so far. And B matching is just like it's just any graph that the degree profile respect B. Okay. So now I claim that we can define like a cut matching game for arbitrary node weighting A. Okay. Like it's just natural way to extend the cut matching game for any node weighting. So instead of working with 1V matching, just work with A matching. Okay, so what will happen? Just start with empty graph like before, and for each round, the cut player choose like left and right set A and B. But I instead of using A and B, I use L and R now because there is this node weighting A, so I don't want to confuse you. We choose AI, Li and Ri, such that L is smaller than R. In what sense? In the sense of A. Like A of the node weighting on L is smaller than the total node weighting on R. And then the matching player will just choose bipartite A matching between L and R. So we used to just say that this is one V matching between L and R, but now it's just A matching. On what's the size? Like what's the size of M? It's basically the idea is like to mesh everything in L. So meaning that like if this is like a node here, and this is 2, 1, 3, 1, then you need to basically now find Mi, and let's say this is Li, this is Ri. So Mi will look like this, right? It has 2 degree 2 here, degree 1 here, degree 3 here, and degree 1 here. This is like example of Mi. Just A matching between L and R such that it basically kind of mesh the idea. Like we used to say that we mesh everything on the left. Now what it means to mesh everything on the left here is just have like certify the total degree, the total capacity of every node here. Yeah.
Are we allowing like fractional edges? Because we allow a node weighting to map to like to the positive or the non-negative reals. So like if I have like a node that's like 0.5.
You can generalize to that too. Yeah. Right. Okay. But now, okay, here, like this is like basically natural generalization of cut matching game for any node weighting. Can you try to suggest me when let's say when A is integral, let's say, can you suggest some strategy that will work in something like A time per round? Yeah, it's not too clear. But the idea is this. The idea is to reduce to what we have seen before. And the idea is for every node V, let's say that you make AV copies of vertices. Kind of if this node has weight 2, split it into two nodes. Okay. And now once you split node V to AV many copies, now just put, for each of the copy, just put like a weight 1 to every node. Okay? So if you say that V prime is a resulting set of vertices, now the size of V prime is exactly the total size of A, the total sum of A. And then you can just run the normal cut matching game on this thing, on V prime, which has size A. So the time per round is of size, is times something like A, because V prime is of size A. At the end, you're gonna get that one V prime is expanding in this graph, G prime. And once you have that, once you are done, then contract all the copies. All the copies of V to V. Then you can see that like this process, if you do this process, it really just gonna be like the matching player here will kind of correspond to some matching in G prime. And it really just mirror each other like this. And you can solve this. Okay. So yeah. So the time in route I takes this time, which is something like AI. So but the point is that AI can be actually very huge. So sometimes we're not satisfied with this. And yeah, I'm gonna mention like how to, like tomorrow I'm gonna mention like that you can actually do it faster. And actually, there's gonna be 2 more extension of cut matching game. The one with deletion and the one with that the matching player can transfer vertices, transfer vectors. I tell you what these extensions are. The extension is gonna be really useful for the algorithm next week. Like next week is about we do hard work to show cut matching game. Next week we're gonna use it to get almost linear time algorithm for expanded decomposition and for something else. Yeah. All right, yeah. See you next tomorrow. Yeah.